Okay, to kick off this new unit on light, we are going to look at this huge question: what is light? If you take a look at the pictures on the screen, you'll notice that light appears in so many different aspects of life. But when we think about it, what really is it? And that's the same question that people were asking historically. What is light? We're interacting with it on a day-to-day basis. We see different things. There's warmth from the sun, all these different elements of color, but what really is light? So, we're going to look at the history here of several different discoveries that led us to our current understanding of light. These different people here on the right-hand side are different key scientists that lead us up to our current understanding. The first, Newton, has this concept that light is essentially small particles or corpuscles that moved in straight lines at high speed, and the different properties of these corpuscles define color. And if you read his original postings, Newton thought that things like red was heavy and strong color, and so those were large, massive corpuscles of light, versus other colors that were small and light. Another scientist, Christian Huygens, imagined that light was a wave, and this would help explain things like spreading out light when it travels through a pinhole, which we would think of as diffraction. However, Newton's more impressive reputation at the time outweighed Huygens, and so the particle theory was more highly accepted at that time. Ole Romer was credited with the first calculation for the speed of light, and thus the concept that it was not an instantaneous thing. As we know, speed is distance divided by time, so to capture something fast, like light, we would need a huge distance in order to have a noticeable time. Romer was observing the moon Io traveling around Jupiter and noticed that the disappearance to reappearance of Io took a different amount of time depending on where Earth was in the seasons. Consider something like winter versus summer. You notice in the picture down here that at one point Earth would be closer and at one point Earth would be farther. So it would take a different amount of time for light to travel that distance. Based on Romer's data, he calculated that the speed of light, if we converted it to current metric values, was about 211 million meters per second. Now, there's more scientists than what are listed here, but the next one we're going to focus on is Thomas Young. Thinking timeline-wise, this is a couple hundred years ahead of the three that we've already looked at. So for a couple hundred years, people are still arguing whether light is a particle or a wave. So Thomas Young was experimenting with light and developed this experiment where he shined light on two slits with a screen behind it. And he was thinking that if light was a particle, then when it hit the two slits, it would travel in a straight line and make two bright bands, kind of like a bunch of tiny BBs shooting through a hole, or like a paintball gun shooting through two holes. They just travel straight and splat on the wall and make two bands. However, when he shined light on these two slits, it produced a pattern of light and dark bands like the picture in the bottom right. So this was very strong evidence that light must be wave-like, because it would be diffracting through the two holes and then interfering, producing this interference pattern of bright and dark. You'd think that this would be enough to just say light is a wave, but it's again this game of whose reputation is better, so it took a while for people to really think that Young had a whole lot going on here. Another important scientist, James Maxwell, was working with the equations for electricity and magnetism. In his ponderings, he combined these equations and found that there was a wave-like solution to combine electricity and magnetism. Essentially, this idea that there was a changing electric field producing a changing magnetic field and vice versa. These oscillations appeared to be able to induce one another. In other words, a changing electric field would induce a changing magnetic field, and a changing magnetic field would induce a changing electric field. Maxwell's calculations showed that these waves would be able to propagate at 2.99 times 10 to the 8th meters per second. Now, if we reword that, that's just under 300 million meters per second, which is rather close to Ole Romer's calculation for the speed of light. And between Romer and Maxwell, other people calculated the speed of light and got values extremely close to this. So when Maxwell figured this out, it was this huge moment of like, oh my gosh, I think this is what light is. Light is somehow this wave-like electric magnetic field thing. The next important person is Max Planck. Max Planck was looking at what the ideal temperature would be to produce the most light. The story goes that he was working in Germany for the government, trying to determine how to best make light bulbs that would be most efficient. Now, what he was looking at was this strange discrepancy between the current theory, which was called the Rayleigh-Jeans law, describing how light would be emitted from hot objects. There was a discrepancy between that theory and reality. The theory, the Rayleigh-Jeans law, described this just weird situation that didn't happen, where you'd get like an infinite amount of radiation at really high energy wavelengths. To fix the theory, Planck posited that energy could only be emitted by objects in chunks, not simply any amount. This fixed the problem. So looking at the graph in the bottom right, the dark black line there, Planck's radiation formula, fit the actual observed data nearly perfect. But Planck had no idea what this concept of energy chunks or quanta really meant, and he hated that. He had a solution, but he didn't know what it really meant. The final person in our chain of scientists is Albert Einstein. Einstein was trying to explain how photoelectric cells or solar cells could produce an electric current when light was shined on it. Einstein realized that the behaviors he was seeing with these photocells could only be explained if light were not really continuous waves, but wave packets or quanta. Essentially a chunk of wave, which is a really weird thing to say because the word chunk implies particle and the word wave is not particle, it's a wave. So Einstein has really stumbled here that light is somehow wave-like, but also particle-like. Now looking at the picture in the bottom right corner, the idea was when you shone light on these photoelectric cells, the properties of these electrons that were ejected were completely defined by the color or the wavelength of light. If red light were shown on these cells, it didn't matter how bright the red light was, it wouldn't eject electrons. But if you shone violet light, then electrons were ejected with a high speed, even if only a low intensity were shown. So the concept was that these short wavelength, high frequency violet colors had more energy per packet, per chunk of wave than the red. Again, the whole concept here is that light is somehow behaving like a particle, that as these light particles were hitting the surface, they were ejecting electrons in a way that was very particle-like. So again, Einstein reveals this wave-particle duality to light, that it is somehow wave-like but also particle-like. Einstein actually won the Nobel Prize in Physics for this discovery. So we have all these separate pieces. How do those all collapse together? I'm sure that you guys are sensing a bunch of the pieces already, but to put it all in perspective, light is an electromagnetic wave that travels at 300 million meters per second. The different frequencies of this wave define the entire electromagnetic spectrum. Visible light is just one slice of this whole spectrum. The electromagnetic spectrum consists of radio waves, infrared waves, ultraviolet X-rays, gamma rays. Our eyes are only able to perceive this tiny little piece of the whole spectrum of electromagnetic waves. Now, these are extremely unique waves. Prior to this, all the waves that we knew of were called matter waves. In other words, there was a medium, some kind of material, that the wave traveled through. So think about like sound is a wave through air, or a water wave is this disturbance that travels through water. But now we're talking about waves that don't require a medium. The fields, the magnetic and electric fields, are the things that are oscillating. They don't need a medium to oscillate in. The other unique part of this is that these waves are emitted in discrete quanta or packets that we call photons now. And this reveals the wave-particle duality to light, that somehow light is both wave and particle at the same time. It's not one or another, it is both. And that these wave-particle things travel at this speed. Now, just one reflection piece here. The equation that we discovered back in the waves and sound unit of velocity equaling frequency times wavelength is still applicable here, since light does have the wave-like nature. The nice thing is just the v, the velocity of light, will always be that 3 times 10 to the 8th meters per second, or 300 million meters per second. So we have this question: what is light? And all these different pieces that have collapsed together for our understanding of light being this unique kind of wave, but also a particle at the same time. It's pretty awesome.